Hi, in this video, we want to take a look at non-parametric statistics. Okay, so non-parametric statistics, we're in the situation where we don't have an assumption or the needed assumption is incorrect to do regular statistics. So in parametric statistics, what's going on is that we have assumptions. And sometimes those assumptions, I look at my data and like, this doesn't work. Or for background knowledge, theoretical understanding, I know that those assumptions just don't apply to the data I'm working with. Well, what can I do? Well, I still need to make a statistical inference, right? My job is to like figure out things using data. So I need a different tool. Non-parametric statistics is that tool frequently. All right, so in non-parametric statistics, what we're going to do is that we're going to work with our data in a way that I need fewer assumptions about what's going on. And so by having fewer assumptions, I'm less likely to make a mistake in assuming that something is the way it is. Something that's really cool about non-parametric statistics is that frequently, if you had to, you could actually compute the statistics by hand if you wanted to. I didn't believe it at first. When I took my non-parametric stats class, I actually tried it out. It was in the textbook, and I was like, wow, this is amazing. You could actually do so if I was on a desert island and I had to do statistics to get off that desert island, I would be using non-parametric statistics. All right, so parametric statistics have assumptions. So that's the big thing. So everything that we've talked about for statistical inference has had some kind of assumption built into it. And we might be in a situation where the assumptions needed for the inference, such as the normal distribution, just don't hold. All right, so let's say that, you know, let's say that we're doing a test that requires a central limit theorem, but my data clearly does not hold to the central limit theorem. Maybe the data I have, how it was collected, my subject matter experts indicate that the central limit theorem does not apply. Well, then I can't use any theoretical test that depends on the central limit theorem. All right, so frequently this will be because of the shape of the distribution is not a bell curve, or I have a small sample size. All right, so then we can use non-parametric statistics. And so, which uses fewer assumptions about our data. All right, so there are like four major levels of data. All right, the lowest is nominal data. And so here, these are just classifications. So this will be maybe like Bob, Jane, Jim, or maybe North Dakota, Florida, Washington. Like there isn't any like natural ordering of what's going on. Now, ordinal data is data that there is like an order to it, but we don't have a sense of distance. So if we say first place, second place, third place, well, there's a first place and there's a second place. It might have been it was neck and neck up to the very end, and first place just came out a little bit ahead, or there might have been a huge gap between first place and second place. We don't know. When I say this person got first place, this person got second place, I don't know if it was they were sprinting at the very end, going crazy, head to head competition, or if the first place absolutely blew away everybody else. We don't know when we say first place, second place. Ordinal data is that type of data where I know which one is like greater, which one's lesser, but I don't know by how much. Another example is when you deal with data that I was actually using this for work yesterday, is that like very high, high, moderate, low, very low, or very likely, likely, neutral, unlikely, highly unlikely. Though that's also ordinal data. So that's Likert scale data. And this is, is all over the place in terms of surveys and responses and things like that. All right, so ordinal data do not have like numeric value. So the main thing is I don't know the distance between things. So when I say that, when somebody says they're highly likely, and another time they say it's just likely on like some like internet response survey, you don't know if it was like they're barely highly likely or if it's like solid, highly likely. You don't know if they're, if it's just a little bit better, they would have gone from likely to highly likely, or if they were just a little bit above, neutral. And that's ordinal data. So we don't have a sense of the actual distance. We have ordering, but we don't have the distance between them. Now, the next type of data we have is interval data. All right, so here, frequently, so in a lot of cases, interval data and ratio scale data, operationally in statistics, are usually practically the same. It's not a big difference for the type. We usually handle it the same. Usually we'll just code this as numeric and call it a day. Interval scale data. All right, with this type of data, we have a sense of distance between things. Now, ratio scale data, we also have a sense of distance, but we have something that's called a true zero. Now, what is the difference? So when I talk about interval scale data, we don't have an actual true zero coming up. There aren't a whole lot of examples of these. There are a few others. The biggest ones are temperatures, that we could measure temperature with Fahrenheit, Celsius, and Kelvins. And we're measuring the same thing, but we're applying different numbers. Now, when I say I'm measuring in Celsius, I have an idea of the difference between what's going on. I have an idea of distance between them, but I could rescale, and the zero is different. So the 0 Celsius is different than 0 degrees Fahrenheit, which is different from 0 degrees Kelvin. All right, so if I have numeric data where the zeros are not consistent, so if I say 0 on this scale and that's a different measurement than 0 on a different scale, then I have interval scale data. Ratio scale data is where 0 on one scale is the same as 0 on another. So example for this one is if I'm measuring in pounds and kilograms, 0 pounds is the same as 0 kilograms. 0 meters is the same as 0 feet. The zero, if I get a 0, it doesn't matter what particular type of what unit I'm using for measuring, I'm going to get the same one every single time. I get 0 every single time. All right, so nominal scale data, really, we just know the difference between our data levels. Ordinal data, we know the difference between the levels of data we have, and we have an order to them. Interval scale data, here we know the difference between our data values. We have an order to them. We have an idea of distance between them. So now another one is that we have subtraction. And now ratio scale data takes it a little bit further, and we can pull in division at this point. So there's a hierarchy. Nominal is the lowest, then ordinal, then interval scale, then ratio scale. Yeah, the textbook calls this cardinal data for interval and ratio. I use a lot of times, like when you're working with R, it's coded as numeric. In Python, it'll be coded as a float. All right, so here let's talk about the first non-parametric test that we're going to talk about, the Sine test. Okay, so what we're going to do is I want to evaluate if we'll start out easy. I want to evaluate if the central tendency is equal to 0. Now, when I say central tendency, now I'm going to be a little bit more flexible with what I call central tendency. It will so for here, I want to know, is the central tendency equal to 0 or is it not? And what I'm going to do is I'm going to convert all of my data to plus or minus. If it's a positive value, I put a plus. If it's a minus value, if it's a negative value, I put a -1. And then I'm going to work out the probability distribution of the pluses and the minuses. And if it works out that if I add them all up, it's close to 0, then I say my central tendency is equal to 0. How I can extend this is that we go ahead and if I want to say the central tendency is equal to a particular value, I subtract off that value from my data. Now, to get the probability distribution of the Sine test, we're going to be using the binomial distribution. And we're just using the sign, and we're not using the actual value itself, just the sign of it. And so here's the computation aspects. So really, for the purpose of this video, we're just going to go in, we're going to drop this into R, we're going to drop this into SAS, we're going to drop this into Python, and we're going to let it work it out. We can also do, one-sided tests. So here we're talking about two-sided tests. Here we're doing one-sided. If we get enough negatives, we'll say that's less than the hypothesized value. If we get a lot of positive, we'll say that it's greater than the hypothesized value. This one's really cool because you can do this pretty easily by hand. All right, so computing the p-values for the Sine test, the previous slides, they showed you how you would do that using the normal approximation, the binomial distribution. If n is less than 20, then the exact binomial probabilities should be used instead of the normal approximation. And to do that, we need to just compute out what's the likelihood of seeing that extreme or less. If you're using R, it does this immediately for us. We don't need to worry about it. All right, so now the Wilcoxon assigned rank test. All right, what we're going to do is I'm going to convert my data to ranks. So my lowest value will be, so we're going to convert everything to, I'm going to rank all my data, and I'm going to preserve the sign. And what I'm going to do, I'm going to run statistics on those values. So I'll have like 1, 2, 3, 4, 5, 6, and so on for my actual data. And so my hypothesis is going to be, hypothesis test is for testing to see if the median is equal to a particular value. And the Wilcoxon signed rank test is analogous to the paired t-test. It's non-parametric because what I'm doing, I'm taking my data, I convert it to the rank of the data. So I don't go by the actual values, I go by the ranks. And so here, I don't care about the actual distribution that my data came from when I work this out. So that's why it's non-parametric. So I'm going to arrange the differences. So this is for a paired test. A paired test. I'm going to arrange the differences in order of absolute value. I'm going to count the number of differences with the same absolute value. I'm going to ignore the observations where the difference is equal to 0 and rank the remaining from 1 for the observation with the lowest absolute value up to n for the highest absolute value. If there is a group of several observations with the same absolute value, then the lowest rank in the range is equal to 1 plus r, the highest rank in the group. So it basically ties. This is just specifying how to do ties. Every software system will handle that. Different. So when I have ties in my data, I could go, so let's say that second place, third place, fourth place are all tied together. Then I could go with a 2. I could go with a 3 for all. I could go with a 2 for all of them. I could go do a 3 for all of them. I could do a 4 for all of them. I could randomly assign. All these have advantages and disadvantages. The help documentation in whatever software you're using will specify how to say what you want. My opinion is you probably should just use the default for your software. I personally prefer the the average rank when you've got ties going on. All right, so now the Wilcoxon Sine rank test with the normal approximation. All right, so what we're going to end up doing is after I take my data and I convert it over to ranks, now I know that my data is like the integer values like this. And statisticians have sat down and they've worked out the probability distributions of this. And so since I know the probability distributions of what's going on, I know the expected value, I know the variance. As long as I have sufficient sample size, I can go ahead and use the central limit theorem, that is the normal distribution, to approximate the distribution of ranks. And so I'll go do that. Here is the expected value. And now everything about this assumes that there's no ties. In my work, I haven't seen ties be much of an issue. The more advanced softwares will take care of this for you if it's an issue. And so here if this is so here all right, so what's going on with this? This R1 is going to be the value I get. Here is my expected value. Here is an adjustment for using the normal approximation. And here I'm dividing by the standard deviation. And so this works out. This is when there's no ties. This is a more advanced one for when there are ties. Yeah, and something I find interesting about these, when I took non-parametric statistics, I had to work out all these distributions, pencil and paper, and these are actually pretty easy to compute. I was really surprised by that. All right, so, and we're going to go through the same scheme. If my test statistic is greater than a cutoff, reject the null hypothesis. I can get my p-value by getting the shade region, and then I reach my conclusion and I share my results. All right, so the Wilcoxon rank sum test. This is also non-parametric. It's analog to the t-test for 2 independent samples. So previously we were looking at paired data where I take the difference. So now what we're going to do, we have 2 independent instead of paired data sets. And everything works out to be conceptually the same, but the computations and how we get to the test statistics and how we get the p-value is slightly different. All right, so what I'm going to do, I'm going to combine the data for the 2 groups and order the values from highest to lowest in terms of the measurements I'm interested in. Now, when I do this, what I need to do is I need to keep track of which data point comes from which population. So I've got 2 populations. I want to check to see, do they have the same central tendency? So what I'm going to do, I'm going to take my data, think about it doing this in Excel. I'm going to have a spreadsheet. I'm going to have one column is the population it's coming from, like group A, group B. The other column is the measurement. I sort by the measurements and then convert to ranks. And then when I convert to ranks, I connect those back to the population. Now, so I assign ranks to the individual values. And what I'm going to do, I'm going to look at, do I have higher rank or lower rank in a particular group? If it looks like overall they about get the same value of rankings, then it doesn't. Then I conclude that they have equal central tendency. If a group of observations have the same value, then compute the range of ranks for that group, and as was done for the signed rank test, and assign the average rank for each of the observations in the group. All right, so now the Wilcoxon rank sum test approximation using the normal distribution for two different populations. All right, so I'm going to rank the observations. I'm going to compute the rank sum in the first sample. And now if the rank sum does not equal this, and there are no ties, then I'll go ahead and use this as my test statistic. If the rank sum is not equal to this, and there are no ties, I will use this to compute the test statistic. And the T sub i's denote, those address our ties in the system. And then once I get my test statistic, I go over to the normal distribution and I, get my get my p-value, make my conclusion, share my result. All right, so here we want to do this only if both populations have at least 10 observations and if we believe that there's an underlying continuous distribution for them. All right, now the Wilcoxon rank sum test is sometimes referred to as the Mann-Whitney U test. This is how I learned it. In class, I learned it as Mann-Whitney U. But if you're in R and you're running the test, you'll be using the Wilcox.test function, just let you know. All right, so the test statistics for the Mann-Whitney U test is based on the number of paired observations, one from each sample, such that one population is less than the other. And the choice between using the Wilcoxon rank sum test and Mann-Whitney U test is a matter of convenience. And usually you get about the same result either way. Overall, though, when you're doing parametric tests and non-parametric tests, in general, you will reject the null hypothesis more frequently with parametric tests than you will with non-parametric tests. So non-parametric tests, you are more prone to failing to reject the null hypothesis. All right, so summary. The main advantage of non-parametric tests is that we don't have to rely on assumptions, that I can take my data from a much wider range of values and their value types, a wider range of distributions, and still be able to run things. Now, one drawback of the non-parametric procedures is that some power is lost, and so that's referring to how when I do non-parametric tests, I'm more prone to failing to reject the null hypothesis. The Sine test and the signed rank test are non-parametric analogs to the paired t-tests. And the Sine test is that very simple one where I take my data and I just break it into two groups, positive and negative, plus one, negative one, and then I run binomial distribution to figure out my p-value. Now, for the signed rank test, the magnitude of the absolute value of the difference score as well as the sign is used for performing the significance test. The Wilcoxon rank sum test, or the Mann-Whitney U, is an analog to the two-sample t-test for independent samples. And here we're using ranks to get that going. That's all I've got for you. Take care and goodbye.